Welcome back. So, in today's video lecture, we will look at the Lifshitz approach, okay, for calculating the Hemaker constant between any macroscopic body using the by measuring some bulk properties, right. So, this will be a macroscopic approach, okay. In previous lecture, we dealt with the pairwise interaction based on the van der Waals force between macroscopic body. The one of the assumption that we made was there was no third body interaction, right? There was no third body interaction. So, which means that the two macroscopic objects were kept in the vacuum, right. So, there is no molecule between two macroscopic object. So, based on which we did the pairwise interaction calculation and we obtained the van der Waals equation, right. But what if there is a medium, let us say if two objects are kept in the medium which can be liquid or gas, right. So we are going to look at the Lifshitz approach to calculate Hemaker constant in this case, right. Let us begin. Yeah. So, as we just now described, we are going to look at the Lifshitz theory, which is nothing but a macroscopic approach. Okay. This is because, let us say, in the previous lecture, we talked about we discussed the pairwise interaction, which is additive, okay, based on the assumption that there is no molecule in between. So, we only considered the pairwise interaction between the molecules or the objects between the macroscopic objects, right. But the problem here is we actually have ignored the third body interaction. Let us say in between, let us say if we incorporate this two macroscopic objects into the liquid medium or gas medium, so there will be molecules in between. Okay, what if the molecules carry dipoles within it? There can be it can be dipoles, permanent dipoles or induced dipole within it. Then there can be it can actually interfere with the van der Waals interaction, right. So the pairwise additivity, this property is no longer valid in such situation. So, we have to look at the approach, different approach to calculate the Hemaker constant in such case. So, if we incorporate this third body interaction and try to obtain the solution based on the microscopy theory, which will be little bit more cumbersome and complicated. One has to use the molecular simulation, right, to compute the the total energy of the molecules present, right. So, the other approach which can be used by measuring the bulk properties, right, such as dielectric permittivity and the refractive index. So, when we say bulk property, which means that the theory assumes the continuum approach. Okay. So, the molecular theory is no longer valid in this case. So, all you can do is just measure the bulk properties such as dielectric permittivity and refractive index, based on which you can actually calculate the Hemaker constant. So, that is the idea proposed by Lifshitz in his theory. Okay. So, that is exactly what we are going to look at. So, when I say macroscopy theory, you can actually ignore the some of the uh, the parameter, that is polarizability and ionization frequency, which are very much required when you want to carry out the calculation using macroscopic approach. Okay. But in this macroscopic approach, these two you don't need to really worry about these two parameter, right, because you don't need to really measure and worry about these two parameters because we are not considering the molecular approach, right. We are only looking at the macroscopic approach in which the theory assumes the continuum approach, right. Yeah, it is based on the continuum approach. So, here we will look at the so let's say we have material 1, material 2, they are interacting through the material, I mean through the medium which is numbered as 3. In such situation, the non-retarded Hemaker constant. So remember, when I say non-retarded Hemaker constant, this implies that it includes the third body interaction as well. So the regular molecular theory, the approach based on the regular molecular theory is called retarded Hemaker constant, because that actually ignore the third body interaction. Whereas non-retarded Hemaker constant, meaning it is a macroscopic approach proposed by Lifshitz, in which the third body interactions are considered, very much considered. Okay, so this is what the Hemaker constant. So this equation has got two part. One is the real part of the permittivity, and another one is based on the imaginary permittivity based on the imaginary frequency, okay, which also involve the integration and all that. So one has to evaluate this equation, solve this equation to get the Hemaker constant. The permittivity, at different imaginary frequency can be defined like this way in a compact form. So which is function of refractive index. So n here is a refractive index, and nu is the frequency, absorption frequency, and nu e is the mean frequency, right. So this is constant. This can be this can vary from material to material, right. Right. All right. So if you want to know more further in details, you can actually refer to these books, right. Uh, so you can understand, if you want to understand the origin of this equation, or if you want to get more insight into this Lifshitz theory, you can actually refer to this book, right. Now if you assume that the material that we deal with, let's say all three materials are assumed to be same, the absorption frequency, that is nu, is same for all three material, then the previous you can actually uh, reduce the level of complexities of the equation that we just now described. So this equation has got no imaginary frequency term, right. So which means it's a simple equation, arithmetic equation. You don't even have the integral in this equation. So it is easy to compute the Hemaker constant by using this approximation. That is, when you say that absorption frequencies of all three materials are going to be same, then you can very well use this equation. This is quite compact equation. So this Hemaker constant is always positive, okay, except for few cases. If Hemaker constant is positive, the van der Waals equation that we get will be negative, always negative, right. But in some situation, so van der Waals, I mean in some situation, let's say when the permittivity of medium is slightly larger than the permittivity of the materials, right. Okay. In such situation, you can expect the van der Waals force between the material can be repulsive, and the Hemaker constant in such situation can be negative, right. So for in a special case, one can encounter this scenario, right. Right. So just a small exercise for you. You can actually calculate the what is known as the Hemaker constant, okay, for the amorphous silicon oxide. So silica you can actually use, right. So in this case, all you need to do is you need to calculate Hemaker constant, right, for the interaction between SiO2, right, SiO2 molecules kept in the medium called water, right. So here the E for water, that is E3 is given, that is 78.5, and N3 is also given, that is 1.33, whereas the N1 equal to E2, so E1 equal to E2 in this case, so which means that it is 3.82. Okay. So one can calculate what is the, so the mean frequency is also being given, uh, is also given in this problem. So one has to evaluate what is the Hamaker constant. So I leave this exercise to you. You can calculate what is the Hamaker constant and comment whether the Hamaker constant, whether it is negative or positive. If it is positive, is it a repulsive force or attractive force? So something, so you need to comment on that. Okay, so in the previous case, we know that there was some shortcoming, right? So let's say the original equation which Lifshitz proposed is itself quite complicated, because you need to know, you need to know what is the dielectric permittivity, real part and imaginary part, and then you need to also integrate it, right? So computationally this is little bit more cumbersome. Okay, and but one can use the approximation, that is the based on the assumption that the absorption frequencies of all three materials are same, almost same. In such case, you have the compact equation, which is actually uh, which doesn't have the in that you don't need to actually calculate the real part and imaginary part. Okay, and you don't have integration. It is a simple arithmetic equation, so one can easily calculate by knowing or by measuring what is known as the dielectric permittivity and refractive index for all these three materials. Now another exercise for you is, you need to find out uh, what technique one can use to determine the dielectric permittivity and refractive index. Okay, because this is going to be the bulk property. So when it is a bulk property, one can use by one can measure by using the technique, right? There are some techniques that measure these properties, right? So you need to understand, find out which technique can you use to determine the dielectric permittivity and the refractive index. Okay, right. Okay, the next approach that we will see is based on the surface energy approach and Hamaker constant. There is going to be a relationship between surface energy and Hamaker constant, right? So that is exactly what we are going to look at. In the previous approach, Lifshitz theory approach, so we know there is approximation, right? So if you use that approximation, but then sometime you may not get the precise solution, right? Because the approximation sometime may go wrong, right? Because you don't expect that in every situation you will have the absorption frequency of all three materials will be same, right? So in such case, can we use some other method, alternative method to calculate the Hamaker constant uh, and the van der Waals equation, right? So van der Waals force, I mean energy, right? Total energy based on the van der Waals force, right, of attraction, right? So that, for that, one has to use this simple surface energy approach. Okay, so here all you need to know is, so what we are considering here is, let's say you have the atoms which are held together in a square lattice, right? So you know that when even though atoms are very closely packed together, there will be what is known as the separation distance, right? That is d naught, that is the minimum separation distance, beyond which atom cannot approach closer than that, because there will be a bond repulsion. There is something called Pauli's exclusion principle, which doesn't allow the atoms to explode or access all the space right? So there will be a boundary beyond which atom cannot penetrate further. So that is nothing but d naught, which is the minimum separation distance, right? So if you know that, when atoms are held together in a square lattice, right, at a distance called d naught, uh, so can you calculate what will be the van der Waals force between the molecules? So to do so, let's say if you know that the energy required to break them apart, let's say if you want to cleave this atom, the crystal structure into two halves, then you can basically what you will know what is the energy required to break them apart. If you know the energy required to break them apart, then you have the answer, that is the energy required to combine them. So energy required to break them apart is same as energy required to combine them. So you know that when you calculate what is the energy required to break them apart, so that much energy was actually uh, used, right, between the atoms. That much energy was imposed, right, when they were held together, right, when they were held together in a crystal lattice, right, and that energy is nothing but van der Waals energy, right. So you can actually calculate based on this by equating the van der Waals energy, total energy, to the surface energy here, because when you break them apart into two, you create two energy new surfaces, right. So two new surfaces, so you will have so there will be two two new surfaces are created, right. For each surface you will have one you can assign a surface energy, right. In that way you will have two surface energy, right. So that means 2 gamma s. So if you equate this equation with the 2 gamma s, you can basically calculate sometime what is the separation distance, minimum separation distance, or Hamaker constant, or surface energy itself, right. So we are going to do this exercise. So I want you to do this exercise. So in this equation, so what is given is the Hamaker constant, right, of helium, vacuum helium. So here there is no third body interaction, so no third body interactions, because our approach is based on by separating them into two, right. Yeah. And in this way, what is the Hamaker constant. The value is given here, which is 5.7 10 per minus 22 joule, right. And additionally you are also given interatomic distance of 16 nanometer, okay. That is the minimum separation distance, which is also which is also given in this problem, right. So what exactly is asked in this question is surface energy. So you need to calculate what is the surface energy. So idea is you calculate the surface energy and then compare the surface energy with the literature value, right. You know the what is the surface energy of helium, right. So you can compare this value with the literature and comment on. If the value is very close, you just have to say yes, this equation you are able to calculate the surface energy based on this equation also, okay. So that is all about the surface energy approach. So we have seen so far Lifshitz approach. Lifshitz approach is the macroscopic approach, right. So here in this approach you use the measurement, you measure the bulk property such as dielectric permittivity and refractive index, right, so using some technique, okay. So when I say bulk property, which means that the theory assumes continuum approach, okay, right. So we are not going to bother about the molecular theory, right, because this approach incorporates the third body interaction as well. Now that is uh, uh, first thing we saw was the Lifshitz approach, and then we looked at there is some complication because one has to measure the real part and imaginary part, and there is also integration and all those things, right? So then what we did is we approximated by assuming that the absorption frequencies of all three materials are almost same. In such scenario, you will get rid of those complexities, right? So you will be simply having the refractive index I mean for all the materials, and permittivities of all the materials that you will be having. So that is the approximation, right? So by simply measuring the refractive index and permittivity, you can calculate the Hamaker constant, right? Right. Next, what we saw was the surface energy approach. The surface energy approach was like, again, it doesn't I mean include the third body interaction, but it is somewhat easier than the Lifshitz approach, okay, because you don't need to really calculate or determine any dielectric permittivity, refractive index and things like that. So all you need to know is the surface energy of the material that you talk about, okay. And if it is between two molecules, same molecules, it is quite easier, okay. So for that case, you can use this approach, okay. So if you know what is the surface energy of a given material, and if you are calculating the van der Waals force between two similar material, right, considering a vacuum, then can you use this approach, right? So this is again measuring the surface energy. So you can actually, if you know the surface energy, you can actually calculate the Hamaker constant, but one has to know what is the minimum separation distance, that is d naught, okay. So based on that, you can actually calculate the unknown, okay. I think you got enough insight into what is retarded Hamaker constant, non-retarded Hamaker constant, okay, based on the Lifshitz theory, right? And we'll stop here. We will continue from the next lecture. Thank you.